Now we are going to discuss the functions, 5 theorems which are important for Board of Intermediate examination for junior intermediate. So before once see these questions, these are most important questions from functions for LAQs. So observe that these theorems, 5 theorems. Now I am going to start the concepts first. The concepts mean that the first concept is that to prove a function is 1 1, consider a function f from a to b. It's a function 1 1. To prove f is 1 1, so take f of a1 is equal to f of a2 implies that prove. Otherwise you can write like this: prove f of a1 is equal to f of a2 implies a1 is equal to a2. To prove on to we use in these theorems, let b belongs to b codomain and show that there exists at least one a belongs to a such that f of a is equal to b. So that means that every element of codomain should have at least one premise, 1 1 onto other. So 1 1 is called injection, onto is called surjection. Bijection means that both 1 1 and onto. Bijection means that both 1 1 and onto. So next one is that when it comes to the composite function, g circle f of circle g. Suppose f from a to b, next point, f from a to b is a function, g from b to c is a function, then g circle f is from a to c. So f is a to b, this is b to c. So this is f, this is g. G circle f is from a to c. That is another note. So next one, composite function is important. Once observe that g circle f, the domain is g circle f domain is the domain of f only. 2. G circle f codomain is codomain of g. Codomain of g. What is codomain of g? Codomain of g is c. What is domain of this one? A. So g circle f from domain of f to codomain of g. You remember this, domain of f to codomain of g. So let us start the first theorem. What is that first theorem? Suppose f from a to b, g from b to c are bijections. Bijection means that they are 1 1 and onto, injective and surjective. What we need to show? So we have to prove that g circle f, we have to show that g circle f from a to c is bijective. Bijective means that 1 1 and is a bijection. Okay. Since f from a to b, g from b to c are functions, I am not considering the bijections. Our functions imply that g circle f from a to c is also a function. So to prove that g circle f is bijective, first we need to prove that g circle f is injective or 1 1. To prove a function is 1 1, first we have to take two elements in the domain and take their images are equal. Let a1 a2 belongs to domain. Suppose f of a1 is equal to f of a2. So what is this one? We have to show the g circle f, right? G circle f of a1 is equal to, so we need to show that G circle F is 1 1 mean that we have to consider their images. Can we write this one as G circle F of A1 is equal to G circle F of A2? Yes, we can write that. That is the definition of composite function. Once observe that G of B1 is equal to G of B2 type. So since G is 1 1, G is 1 1. If G of B1 is equal to G of B2 implies that B1 is equal to B2. This is B1, this is B2. So F of A1 is equal to F of A2. Now F is 1 1, right? When F is 1 1, if the images are equal, then elements are equal. Since F is 1 1. So we have taken G circle F of A1 is equal to G circle F of A2, and we have proven that A1 is equal to A2. Means that G circle F is 1 1. Therefore, G circle F of A1 implies that G circle F of A1 is equal to G circle F of A2 implies that A1 is equal to A2 implies that G circle F is injective or 1 1. Next we need to show that G circle F is onto. G circle F from A to C is onto. So first for that one what we need to do, we have to take one element in the codomain. Let C belongs to C. Since G from B to C is bijective is given, right? But I am using only surjective for that. Due to is a surjection is surjective, then there exists B belongs to B such that G of B is equal to C. So B belongs to B. Since B belongs to B and F from A to B is also surjective, right? Is surjective implies that surjective, then there exists A belongs to A such that F of A is equal to B. Let it be 1 and this one be 2. From 1 and 2, what is that? What is B? B is equal to F of A, right? So G of B is F of A is equal to C. So that implies that G circle F of A is equal to C. So for C belongs to C, there exists A belongs to A such that G circle F of A is equal to C. Therefore, for C belongs to C, there exists A belongs to A such that G circle F of A is equal to C. That implies that G circle F from A to C is surjective. So surjective. Therefore, it is both injective and surjective. Therefore, G circle F from A to C is bijective. This is the first theorem. Let us go for the second theorem. What is that? F and B are bijections. Given F from A to B or A to B, G from B to C are bijections. Once read the question, sir. Bijections. When they are bijections, just now we have proven that G circle F from A to C is also bijection. When the function is bijection, its inverse is also bijective. That implies that G circle F whole inverse from C to A is also bijection. Since F from A to B is bijection, implies that F inverse from B to is also a bijection. Simple thing only. Since G from B to C is a bijection, so its inverse is also bijection. G inverse, right? G inverse from C to B is also bijection. So once observe that, once consider what we need to show that G circle F whole inverse is equal to F inverse circle G inverse, right? So F inverse circle G inverse is from, can you anyone tell that what is this one? So first we have to consider the domain of G, right? What is that? C. Then codomain of F inverse. What is that? A. Is also, because composite function is bijective when the two functions are bijective. So once observe that. So what we need to show? G circle F whole inverse is equal to F inverse circle G inverse, right? Clearly observe that we have to show that two functions are equal. Clearly G circle F whole inverse from A to C, from C to A, C to A, and F inverse circle G inverse from C to A are bijections. And have same domain. So to prove that two functions are equal, first step is that they have same domain. They have same domain. Bijections and have same domain. What we need to show that? We have to show that they are equal. They are equal mean that first we have to show that their domains are equal and their images are equal. For that images are equal, first we have to take an element in the domain. Element in their domain. Let C belongs to their domain. Since G from B to C is bijection, is a surjection. Only I am using surjection, not bijection. Surjection. Then there exists B belongs to B such that G of B is equal to C. So G of B is equal to C means that G inverse C is equal to B. Whenever is needed, I will use that. Since B belongs to B and F from A to B is onto or surjective, then there exists A belongs to A such that F of A is equal to B. It means that F inverse B is equal to A. Let it be 1. Let it be 1 and let it be 2. So we use only these two equations. Okay. Now consider now G circle F of A is equal to, consider, what is that? G of F of A. What is F of A, sir? From C here, F of A is equal to B, right? From 2. From 2, F of A is equal to B. What is G of B? G of B is C, right? G of B from 1. So since G circle F of A is equal to C, implies that G circle of whole inverse of C is equal to A. So the image of C with respect to G circle F inverse is A. Let it be 3. Now consider other one. What we need to show? That F inverse circle G inverse of C. So this is equal to F inverse of G inverse of C. What is G inverse of C? G inverse of C is B from 1. What is F inverse of B? A from 2. Therefore, F inverse circle G inverse of C is equal to A. Let it be 4. From 3 and 4. So these two functions have same domain. The images are equal, right? Therefore, G circle F whole inverse is equal to F inverse circle G inverse. Done. Let us go for the third theorem. Suppose F from A to B is a function. given that I of A from A to A, IB of B from B to B are identity functions. What we need to show? F circle identity function on A is equal to F first step. So two functions are equal. So F from A to B, right? And IA from, what is that? A to A only. So now consider F circle IA is from composite function A to codomain of B. Clearly F circle, this one is, so we need to show that this one is F is equal to this one, right? So to prove that two functions are equal, the domain should be equal, right? Clearly F circle identity function on A and F have same domain A. So to prove that two functions are equal, their images should be equal. For that one we need to consider an element in the domain. Let A belongs to A. Consider F circle identity function of the image of A. So what is that? F of IA of A. What is IA of A? A only. So this becomes F of A. So mean that therefore F circle identity function on A is equal to F, right? So for all A belongs to A. So those are images are also equal. Next we need to show that identity function on B circle F is equal to F. Since F from A to B, IB circle B from B to, right? So what is the, then this is from A to B. A to B because domain of F and codomain of IB. Okay. Now we need to show that their images are equal. Let us take an element in domain. Let A belongs to A. Okay. Consider IB circle F of A. This can be written as IB of F of A. So identity function image is F of A only. Therefore their images are equal. Therefore IB circle F is equal to F. So hence this theorem is easy only. Fourth theorem is also easy. Given that suppose F from A to B is bijection, that implies that F inverse from B to A is also bijection. If a function is bijective, then its inverse is also bijective. So bijective means that can we write F circle F inverse, then F circle F from domain of F inverse B to A is bijection, and F inverse circle F from A to A is also bijection. Now we are going to prove that F inverse circle F is equal to identity function on A. Clearly F inverse circle F from where to where here? A to A, and identity function on A is A to A have same domains. Now we need to show that their images are equal. Let us take an element in A. Okay. So since F inverse from B to A is bijective, so I am using only onto only. Onto implies that then there exists B belongs to B such that how F inverse B is equal to A. That implies that F of A is equal to B. This is the key point. This is the key point, sir. Now consider F inverse circle F of A. What is that? F inverse circle F of A. What is F of A? B. What is F inverse B? A. From above here. So A can be written as IA of A, right? Therefore F inverse circle F is equal to identity function on A. Now the second part is f inverse f circle f inverse is equal to identity function. Same thing, sir. They have same domains. Clearly, f inverse circle from B to B, identity function on B is from B to B, have same domains. Okay. Now we need to show that their images are equal. For that one, let us take an element in domain. Let B belongs to B. When B belongs to B and f from A to B is onto, right? Is it bisective? So I am using only onto. Then there exists this A belongs to A such that f of A is equal to B. So it can be written as f inverse B is equal to A. Consider f circle f inverse of B. Can we write this one as f of f inverse B? What is f inverse B? F of A. What is f of A? B. B can be written as IB of B. Therefore, two functions f circle f inverse and identity function have same domains and the images, they are equal. Last theorem. Here it has two cases. First case, that suppose f from A to B is a function only. Let us take that one as a function. It has two cases. Case one is take f is bisective and prove that there exists a function, another function from B to A such that those two conditions satisfied. First part is easy only. Second case is we assume there exists a function g from B to A and f circle g and g circle f as defined given. We show that f is bisective. So to prove that f is bisective, we need to show that f is 1, 1 and 1, 2. Okay. Those are the things to be considered. So first, suppose case 1, f from A to B is bisective. So if it is bisective, means that we have to show that there exists some function. Okay. F is bisective. So we need to show that there is some function B, some function P, some function G from B to A such that G circle F is F is circle G is equal to identity function on B and G circle F is from identity function on A. And in this case, we have to show all this stuff. G is equal to F inverse. This is simple thing. Since F from A to B is bisective, so inverse exists and it inverse is also bisective. That implies that F inverse from B to A is also bisective. Since these two are bisective, means that their composition is also bisective. That implies that F circle F inverse from where to where? B to B and F inverse circle F from A to A are bisectives. From above theorem, I think fourth theorem, bisectives, and F circle F inverse is equal to identity function on B and F inverse circle F is equal to identity function A by fourth theorem. Therefore, once observe that there exists a function, we need to show that. Once see this one, there exists a function, some function g from B to A such that this one holds, right? So instead of g, just imagine F inverse. So the function we are searching, what we are searching is nothing but g inverse only. There exists a function, that function can be anything. So I am taking that one as F inverse. Therefore, now take therefore F inverse from B to A exists satisfying the given conditions, given conditions. So in this part that G is not nothing but F inverse. Therefore, in this case G is equal to F inverse. This is simple thing only. Case 2 mean that this is the little bit tricky. You have to be more aware of that. What we need to show that, assume that there is a function. There exists a function. There is a function G from B to A such that G circle F is equal to identity function and F circle G is equal to identity function on B. Okay. What we need to show? We have to show that F from A to B is bisective. And in this case, and bisective, and G is equal to F inverse. So to prove that F is bisective, we need to show that F is injective, F is 1, 1. For that one, we have to take two elements. Let in the domain, let A1, A2 belongs to A, and F of A1 is equal to F of A2. So we have to always use these two, sir. So for that one, I am applying G on both sides. G of F of A1 is equal to G of F of A2. Can we apply like that? As G is a function. So what is G circle F of A? G circle F of A1 is equal to G circle F of A2. Let it be 1, sir. So what is G circle F? Identity function on A is equal to identity function on A from 1. What is the identity function image? Image is as it is. So F of A1 is equal to F of A2 implies that A1 is equal to A2. So it means that F from A to B is 1, 1. Next we need to show that F from A to B is onto also. Onto means that let us take an element in the codomain. Let B belongs to B. So let B belongs to B mean that implies that G is from B to A. B to A is considered, right? B to A. So G of B is equal to A belongs to A. Since G is a function, so it has image, right? So now consider F of O. Therefore F of A is equal to, what is A now? F of G of B, right? What is F of G of B? That is F circle. This is consideration only. F circle G of B. From to 1, F circle G is equal to here, identity function on B. So that is equal to identity function on B. Identity function on B means that B. What is there? Therefore F of A is equal to B, right? So for B belongs to B, F of A is equal to B. Therefore for B belongs to B, there is A belongs to A such that F of A is equal to B. That implies that F is onto. Next to third case is what is that? We have to show that G is equal to F inverse. That G is equal to F inverse mean that they should have same domain, right? Clearly G from B to A and F inverse is also from B to A, because F is from A to B means that its inverse is from B to A. Have same domains. What we need to show that? Same domains. Let their images should be equal, right? Let B belongs to B. Since F is bisective, right? I am using only onto. Since F is onto, for B belongs to B, there exists A belongs to A such that F of A is equal to B. So it means that F inverse A is equal to B. F inverse B is equal to A. Now consider, so F inverse B is equal to A. So image of F inverse is A. So we need to show that G of B is also A. G of B is equal to G of, what is B, sir? B is nothing but F of A. It can be written as G circle F of A. What is G circle F of A? That is given as identity function on A from 1 on. So identity function on A is A. So therefore G of B is also A, and F inverse B is also A. They have same images. Therefore G of B is equal to A, and F inverse B is equal to A. Therefore G is equal to F inverse, hence proved. All the best. Take care. Thank you.